Hi everyone. We have another talk here before the big break, and I think most of you have a little bit of experience with malware. If you find something, a virus or something, you know it's there, but if you don't find anything, can you say the machine is clean? I have a security researcher here, Joanna Rutkowska, and she can answer the question, I think. Please give her welcomes.
Welcome, everybody. The title of today's speech is Stealth Malware. Well, the original title was supposed to be Can Good Guys Win? But actually I decided to change it in the last moment to Stealth Malware towards verifiable operating systems. So basically that's going to be about what we need to do with our operating systems to make them verifiable. And what does it mean verifiable? It means that we can actually prove that they are not compromised. So let's start with some basic stuff. So stealth malware, it's usually what everybody understands as rootkits, backdoors, keyloggers, stuff like that. Stealth is a key feature here because stealth means that actually antivirus programs, legal processes, administrators can see it, right? So actually, we should never know that we have ever been infected. So we have a little paradox here. How can we actually know what's going on in the wild if actually we don't have good mechanism to detect it? So today, it's actually very simple because today we actually we count that the malware is buggy. So we have a bunch of hacks. If you look at our antivirus industry, we have a bunch of hacks which try to detect various, well, let's say, compromising techniques in kind of a chaotic way. It's actually true that if we don't detect anything, that doesn't mean anything. This is nothing good, right? Because we want a systematic way to verify that the system is clean, and we don't want to have just a bunch of temporary, just a bunch of hacks which just proves nothing. There are 4 myths which I often encounter about stealth malware fighting, which many people believe in. Myth number 1, this is the most popular one. If you want a definite way to detect malware, we just need to remove the disk from a machine and analyze it on a clean computer. Or we need to boot a system from a clean CD or whatever. It's surprisingly many people believe that this is true. But of course they forget that there are malware which can be non-persistent, and also they forget that we can have malware which is persistent, but the persistency is not on hard disk, but it's actually in some other resources like in BIOS, PCI, ROM, and similar stuff. John Heisman did some work in this area quite recently. So basically, analyzing hard drive is not a good way to detect malware in general. Of course, we might find something. We probably find 80% of malware this way, but if we don't find anything, that doesn't mean anything. So myth number 2 is, well, every malware needs to call phone home, right? Or needs to leak some data, needs to listen for some commands, so some kind of communication needs to be deployed, right? So the easiest way is to forget about operating system verification, forget about operating system at all. Just look at the network traffic, analyze the traffic, and detect every single malware, right? And of course, this is not true because we have various covered channels which could be used which are more or less stealthy, but some of them are virtually impossible to detect in practice. So a little digression about covered channels to make it clear for everybody. So we have this server over here. Let's say it's compromised. Let's say it's some kind of backdoor installed here. Let's say attacker wants to control it in some way. So there's lots of traffic to this server. Well, that's because it's a server, right? So as we see on the next slide, on the next two slides, there are various ways in putting our covered channel in this legitimate traffic without generating any extra traffic. This is the very simple and very bad example, but it gives some idea. This is if we wanted to send requests to a HTTP server. We see the hidden information here, but of course this is very basic and trivial to detect. So another example is Nushu. Actually, I presented Nushu in this very room 2 years ago. And Nushu is a passive covered channel, meaning that it was implemented in Linux kernel and was sitting in Linux kernel and was only changing outgoing packets. It was changing the ISN field of TCP SYN packets. And also, of course, it was, of course, taking care of changing the ISN field when packets were transmitted from the host, and when ACK packets were coming back, the ISN field was changing back, so the connection wasn't broken. And here we see the scenario for Nushu. But there are two scenarios. One scenario is the classic scenario with server, which was 3 slides ago, and this scenario is this scenario for client computer. So we have a Nushu sitting here, and we have a compromised router or something like this, which observes the traffic and gets the information from the ISN numbers. And when I was presenting Nushu 2 years ago here, there was Stephen Murdoch sitting in the audience from Cambridge Computer Laboratory, and actually a few months later he found several problems with Nushu, which allowed for its detection. And one of the problems was that actually the ISN numbers with which Nushu replaced the ISN they were more random than the original Linux ones. There were some other mistakes which I made because I'm not actually an experienced cryptographer. But also Stephen proposed a way how to improve Nushu, because he did a detailed analysis of Linux kernel ISN number generator, and not only Linux but also BSD, I think. So he proposed how to improve it so that it actually mimics the original generator, right? But the question is, yeah, this is about improving Nushu. So now the question is, does the improved scheme is actually totally undetectable? Well, probably not. Probably in theory, we can imagine a very sophisticated statistical test of the random number generator in kernel, which would, well, we can imagine a very sophisticated statistical test which would reveal differences between this generator in kernel and my generator in Nushu, right? But this is only theory. This is maybe possible in lab when we have Nushu, we can generate 100,000 packets, we can analyze them. But imagine deploying this kind of detection in your corporate network. This will not work because we will have to know, well, imagine we have this network and we have this gateway, we want to put NIDs here and we want to implement this detection in this NIDs. We need to have statistical models of all ISN random number generators in our network. This is unfeasible in practice. So that was myth number 2. It was about that it is possible to detect malware by just looking at the network traffic. The next myth is that actually, to detect stealth malware, well, we need to look at hidden objects, right? So we have all those hidden process detectors, we have hidden threats detectors, not so many. We have, of course, lots of hidden files detectors, hidden registry keys detectors, etc. Well, because if something is stealthy, it means that something needs to hide something, right? Well, of course not, because it's possible to create, well, I call it stealth by design. And I gave example of such rootkit 1 year ago at Black Hat Federal. It's called DeepDoor, and DeepDoor was built in such a way that it does not create any objects in the system. So it doesn't create processes, it doesn't create threads even. It has its own implementation of TCP/IP stack. It has its own implementation of useful shell commands like ls, ps, get, put, etc. Actually, it's pretty easy to have this TCP/IP stack implementation, even though many people think it's not that easy, because we have a lot of open source TCP/IP stacks for 8-bit microcontrollers and 16-bit microcontrollers, and they are pretty useful for this purpose actually. So I demonstrate this DeepDoor, and well, it offers all the functionality which classic rootkit does, which classic rootkit like Hacker Defender does, but still it doesn't create anything. So there are no hidden objects in the system. So looking for hidden objects doesn't make much sense to detect this kind of malware. And finally, myth number 4. Well, we just need to deploy efficient prevention technology, like kernel prevention, like GR security, or driver signing for Vista, and many others, or secure level in BSD. Thank you. And we can forget about rootkits, right? Because our kernel is secure. Or maybe malware can do something with processes, but we don't care that much because our kernel is secure. Well, of course, this is not true, because every single prevention technology I can think of has been, at least once in the past, has been proved to be bypassable. And also, even if the technology was, even the prevention technology, kernel prevention technology, to make it specific, was perfect, we still have, we can never eliminate possibility that there will be, for example, a buffer overflow in graphics card driver, or network card driver, or some antivirus kernel component, as we saw some time ago. So prevention is a very good thing. I'll be talking about it. Oh yeah, this is it. So we've got GR security bypass, SL Linux bypass, OpenBSD secure level bypass a few months ago, Vista kernel driver signature bypass, and others as well. So the moral is that we cannot rely on prevention technology only. I'm not saying this is bad. Most of those technologies are very good, and it's a very good idea to have them, but I just want to say this is not enough. Yeah, it's surprisingly many people I talk to from security community, they don't distinguish prevention from detection. So I intentionally put this slide to make it even clearer. Prevention is different than detection. Prevention is all we do that the attacker doesn't get into the system, but detection, on the other hand, doesn't care much about what we did in the past. Detection is just to answer one question. Is the system clear or not? I'm looking for a slide which would be useful here. Okay, let's go with the slides. So in my work, I focus on detection. So I'm not going to prevent installation of malware. I'm just going to try to find out whether the malware is in the system or is not. And I believe that the proper way of doing this is that we need a systematic verification of running operating system. And I stress also the word verification, not really detection, because detection is that we are looking for something, like we're looking for malware, while verification is ensuring that the system is intact. Okay. Yeah, I've got some problems with seeing those slides actually because the light is very bright here. The main problem, the main difference between detection and prevention is that prevention, if we rely only on prevention, the prevention needs to be perfect all the time. If we deployed prevention in 2003 and suddenly last week somebody discovers a bug in our prevention, that means we don't know whether we were infected over those last 3 years or not. And it's like if we relied only on this prevention, we can as well reformat all the system, reinstall the system. On the other hand, so prevention is something which should be perfect from the very beginning. Detection, on the other hand, could be improved increasingly because detection is only here and now whether the system is okay or not. When I detect that my detection is not perfect, I can improve it. I can run it tomorrow and see whether the system is okay or not. It makes sense. With prevention, it doesn't. Also, many people focus on things like how malware gets installed. Exploit, malicious employee, stolen password, whatever. Again, this doesn't mean anything for detection. This is completely irrelevant for detection. This is only relevant for prevention. Okay, so actually I'm talking about the system compromise, but I haven't defined actually what system compromise is. So I'm going to give you my controversial definition of stealth malware or system compromise. Because it's controversial because most antivirus people don't agree with it. So system compromise or stealth malware would be anything which subverts, that's the keyword, either operating system or some sensitive applications like a web browser or email client or whatever, or KeePass. And it does it without user consent, and there is no documented way to find out that the subversion took place. And that's all. This is a narrowed problem from the general problem, which is malware fighting. This is a very narrowed problem. And if we look at the example of modern operating system, that could be Windows, Linux, BSD, whatever. If we apply this definition from the previous slide to this picture, then we will see that. Okay, maybe in a different way. Those things on this picture are things which could be subverted. So if any of those things on this picture are changed by some other piece of software, this piece of software is classified as something which compromises system or as stealth malware. So I classify then those ways of compromising into 3 categories: type 1, type 2, and type 3. And also I'm including type 0, which actually is not a compromise. It's an example of what antivirus thinks is a malware, but it's not actually a compromise. Because it doesn't follow the definition which I just introduced. So type 1 malware is just an application. It's just an application, a process, running process in the system, which doesn't subvert anything. So it doesn't interact with any other application, doesn't interact with the kernel in any undocumented way. Of course, this could be a botnet. This could be a botnet which just opens some TCP port and listening for some commands. But still, it opened the TCP port using a documented API. It doesn't do anything to other components of the system. It doesn't subvert any application, doesn't subvert kernel. Of course, it still could be, I don't know, could be an application which deletes all my files in my home directory. But still, it uses documented API to delete those files. It's just a feature of this program, right? To delete the files. Just like nobody will say that RM is a malicious program, right? Or actually, RM is not a program, but command, but something similar, right? Well, of course, still we can discuss that some programs might be bad and some programs might be good. But this is beyond my interest. Those programs do not compromise the security of the operating system. They might introduce malicious behavior, but, well, this is a different thing. If I decide to install it, it's a different problem. Well, of course, I call it type 0 malware just to make this classification complete. And of course, type 0, this is actually a favorite topic of research for all antivirus programs. Okay, so now I'm gonna talk about three types of malwares: type 1, type 2, and type 3, which do compromise operating system. So first we have type 1 malware, and type 1 malware is defined as malware which subverts things which should never be modified. For example, a code section of kernel or code section of anything. Usually, this should be read-only and never been modified. So we see here the malware which just introduced some hooking or CPU system registers, did some hooking and subverted code. And code is something which should never be modified. Examples of type 1 malware. This is actually the most popular type of rootkits. We've got Hacker Defender, Sony Rootkit, Aproba, and many others. And we think about this from the detection point of view, that should be quite trivial task because, as I said, type 1 malware is malware which modifies only things which should never be modified. So, no easier thing than just detect those modifications. All we need here is a baseline, and this could be just like hash of every code section, or hash of every system binary which is used to create code section, or we just could have digital signatures deployed on every executable. Again, I need to stress here that executable signing is usually thought of as a way to prevent untrusted executables from running on the system. So this is thought of as a prevention technology. But of course, we all know that digital signatures are not a good way to prevent untrusted code execution because, for example, we get all those bugs, and as a result of exploiting something, as a result of running our shellcode, we can introduce arbitrary code. So I don't believe that PKI, that digital signing, is a good way to prevent malware, but actually this is very useful in detecting type 1 malware. If we focus on Windows systems, there are 3 approaches to detecting type 1 malware, which I'm aware of. Vice by Jamie Butler, which tries to find some hooks in functions. System Virginity Verifier, written by myself like 2 years ago, 1 year ago. And PatchGuard by Microsoft, which basically works very similar to SVV, but works in the real time and from... Actually, the only difference is that it actually works in the real time. The idea behind, well, SVV or patchguard is very simple. If we have some code sections in memory, let's say we want to verify TCP/IP.sys text section, what we need to do is to read a corresponding file from disk, which is signed on all Windows systems. So we verify the signature is okay, so we parse the file, we find the code section, we do the fix-ups, and we compare byte by byte with image in memory. If it's the same, then it's okay. If it's not, well, then it's not good. PatchGuard was introduced in 64-bit version of Windows, and it verifies code sections of several images, like TCP/IP.sys, like NTOS-kernel.exe, and several others. And also it monitors IDT, GDT, and SSDT. Again, PatchGuard should not be thought of as a prevention technology because it could be relatively easy bypassed. It has been proved some time ago. Well, because any software which runs with the same privileges as the other one can subvert the other one, right? So it can be disabled. But it's not the point about PatchGuard. The point is that PatchGuard can eliminate, can force the legitimate vendors from using the same tricks as type 1 malware. When I said about type 1 malware here, I forgot to add that lots of antivirus products, for example, does exactly the same type of hooking. To implement host IPS, to implement personal firewalls, etc. And actually sometimes the hooking is virtually impossible to distinguish from the hooking introduced by some rootkits. So the good thing about PatchGuard is that it should clear the playground. It should force vendors not to use those nasty tricks. So that we know that if we detect a modification in code section, that means it was introduced by malware and not by some antivirus product. Okay, so that was type 1 malware. Type 1 malware, think about type 1 malware as a malware which modifies code in memory. And think about detection of type 1 malware basically as comparing what we have in memory with what we should have in memory. So we read the image from disk, we verify the digital signature. This is the key point, digital signature of the image, and we compare byte by byte. I'm sorry. We compare byte by byte with the code section in memory. Dobra, okay, type 2 malware. Type 2 malware, well, type 1 malware modified things which should never be modified, so type 2 malware modifies things which are supposed to be modified all the time. So basically that means that it modifies data sections, some data inside data sections. So we see this picture, and we see changes introduced only in data sections. This is very small, it might seem like a very small difference, but actually it's a huge difference when we consider detection, because we cannot have signed data sections. We cannot create a hash of a data section, because a data section, let's say a kernel data section. Of course, there are like dozens of data sections in kernel, but let's say this one. So we cannot create a hash of this data section, because the data inside it are changing 100 times every single millisecond, right? So we cannot just verify the data section is intact, because there are megabytes of dynamic data which are constantly changing. And some examples of type 2 malware. The DeepDare which I mentioned, which was stealth by design, has also been implemented as a type 2 malware. So it didn't hook any code, it just modified some pointers inside and these data structures. And this is a network subsystem of Windows. So there are some data structures which have some function pointers, which points to some functions which handles, I don't know, incoming packet or something like that. And only those function pointers were modified. Actually, deepdir modified only 4 function pointers inside, somewhere inside data section of NDIS. And fighting type 2 malware is a very challenging task. Today we cannot solve it. We have 3 issues here. One issue is to know where to look. Because if we have this like 5 megabytes of data, there are some data which are pretty constant, and there are some data which are changing all the time. Maybe the change of some of those data means system compromise, and the change of others does not. So we need some way to know at which data we need to look at. In case of deepdir, there's a data structure called NDIS open block, which is a binding between NDIS miniport, which describes network card, and NDIS protocol, which describes protocol. So it's a structure which does the binding. So we need to know that such data structure and this open block could be subverted, that there are some important function pointers inside, which could be subverted to create a network backdoor. We need to know where those data, where the instances of those structures are at the moment. So we need to find some dynamic lists of those in these open blocks. And finally, we need, and then we need to look at those pointers. So at specific offsets in this data structure. So this is to know where to look. Because not surprisingly, I chose to hook like some 4 pointers inside this open block, but there are like a few dozens of other places, as you might imagine, inside Windows kernel, which could be hooked to achieve exactly the same, to create a network backdoor. So we would have to have a list of all those sensitive data structures which we need to look at, which is unfeasible today. Okay, the second issue is to understand what we see. So we read those function pointers, and let's say this function pointer says OX804518E7. So does it mean a system compromise or not? Well, it depends. We need to know what is the semantic of this piece of data, and the semantic is a function pointer which should point to some valid function which does something. So we know in this case that we should look at this address and find out whether this address is contained inside a trusted module and belongs to a code section, a trusted code section of this module. Finally, we need to be able to read memory. This might be surprising because we all know how to read memory, don't we? Because computers are just Turing machines, right? This is what I actually just said. And this is also what I just said. And this is about reading memory. So as we know, computers are just Turing machines. So what's the problem in reading the memory? But actually, there are some complications. Because if we think about a software-based detector or a verificator, we usually think about kernel driver or a loadable kernel module, which does this job. Well, alternatively, it might be implemented as a hypervisor to make sure it can be subverted, but it doesn't matter. What matters is that to read the memory, which is occupied by the operating system, and we are just something other. We are a third-party program which tries to access the memory which is occupied by a system. We need to properly synchronize with memory manager. You might think, okay, but we cannot break anything by just reading memory. But actually we can. And like 1 year ago when I was working on SVV, I saw several crashes, system blue screens, just because SVV was trying to read memory without properly synchronizing with memory manager, and that created some very weird race conditions. Also, the other problem is that if we are a program, even assembler, even looking from the assembler point of view, we can only access virtual memory. We don't have access to physical memory. And there was a nice example of Shadow Walker rootkit, written by Jamie Butler and Sherry Sparks, which implemented virtual memory cheating. So even if another program running as root, using machine instructions like move to read the memory, this program was getting a fake contents of memory. So to overcome this, we need to have a way to access page directories, so PD, and some others on 64-bit processors in a reliable way. But to do that, we need to follow CR3 register, and CR3 register contains physical address. And actually, there is no easy way to convert physical address to virtual address without relying on default OS mapping. So we can, some people can say, okay, there's no problem because CR3 points to some address, physical address, and usually on Linux that would be CO something something for page directory. But assuming that the operating system is intact, but attacker could have modified it, operating system virtual memory manager, so the page address to virtual address mapping could be different. So we have also, if not software-based detector, we could consider hardware-based detector. Just recently, it has become very popular to use FireWire to access memory. So FireWire or PCI card, they all use DMA, direct memory access, to get access to the actual physical memory without the CPU. So CPU is here, here's the device, like PCI card, here is memory, and device just directly talks to the memory and gets the contents of memory. This is very good because it's very reliable, and it doesn't require an additional software on the target system. However, we cannot read page without memory this way. And also, I wouldn't be so sure that it's actually that reliable, but this is something I'm gonna talk about later next year. Because of those three things I said, know what to look at, understand what to look at, and be able to reliably read memory, today we cannot systematically, correctly detect type 2 malware. Or in the other words, we cannot verify system against type 2 malware. And that's actually the proper topic of this lecture, towards systematic verification of the operating system. So our goal is to change the design of the operating system a little bit so that it will be possible for us to create a detector, software-based or hardware-based or hypervisor-based, doesn't matter. Actually, hypervisor-based is almost like software-based. The only difference is that it's not prone to implementation-specific attacks. So we want a recipe to create a detector, let's say software-based. Detector which when we run against a particular system on this very laptop, then at this very moment it would return a verdict, 0 or 1. System is clean, or system is compromised, and by compromise we mean type 1, type 2, or type 3 malware. Oh, I didn't say anything about type 3 malware. I'm just leaving it for the end of the presentation. So this is what we want. Of course, still, even if we had such an ideal detector, of course, still we could have type 0 malware, which could be botnet or something like that installed on the system, or something which deletes our files in home directory every other week. But again, as I said, type 0 malware, for me, this is just an application having some weird features, right? But this is not something which compromises the other operating system components. I want to verify that the other operating system components are not compromised. So the biggest problem with creating such a detector or such a verificator actually is type 2 malware. And this is a problem because operating systems are too complex. So we don't know what to check and we cannot reliably read memory. So maybe we could change the rules a little bit. How about if we introduced the following requirement? The following requirement which always should be satisfied in a healthy operating system. The requirement would be the only executable pages in the system, let's say kernel for now, are those which contain trusted code. All other pages should be marked as non-executable. I want to focus on kernel for now because this is not that easy in case of some user mode applications like JIT compilers, binary translators like VMware, and etc. So let's leave them for a moment. So for now, I want this requirement to be introduced into the operating system. Why this is so useful? It is so useful because if you think about type 2 malware, we should think about type 2 malware as a malware which hooks some function pointers in data sections, right? So no matter, of course, we agree all that we cannot verify all those function pointers. We cannot find all those function pointers and verify where they point. So instead, we want to make sure that all the code in the kernel, we want to make it possible to verify all the code in the kernel. So if somebody modified some function pointer and points to some other things, some code which does some malicious things, make sure that we could find out that this is code which is not signed with our trusted certificate. So the complete requirements for the operating system would be, there would be 4 requirements actually. The first would be that the underlying processor must support non-executable attribute on a per page level. For example, AMD 64. Operating system must maintain strong data code separation on page level. So in a clean operating system, there should not be any page containing, well, let's say it differently. In a clean operating system, there shouldn't be any kind of data which is kept on a page with executable attribute set. There must exist some way to verify code on a per page level, and in practice that means digital signatures implemented. How this is actually implemented, I mean how this PKI is implemented, which CAs do we need to trust, this is beyond the scope of this research. This could be like, we could set up in our own detector which certificate authorities we trust and how much we trust, etc. But basically we need some way to verify that on this page, and we need to do this on page level, on this code contained in this page passed or not passed the digital verification. And finally, operating system must allow to safely read raw memory by a third-party program. Or if you want to use hardware-based memory access, Then we need to make sure that paging is disabled and there are no interesting things which are pageable, because there is no access to page out memory from hardware. And the verification procedure would be very simple. For each page, so we need to traverse all the page directory, all PTEs, and for each PTE, page table entry, if given page is marked as executable in this PTE, then check if the code containing this page is trusted or not. So verify the digital signature, for example. How does it look in operating systems today? Actually, the second requirement, code data separation, becomes more and more popular today because as a side effect of implementing anti-exploitation technology, like WXRX, for example. Even in Windows, we can see that slowly. Where on 64-bit version of Windows we have kernel stack, page pool, and session pool marked with an NX bit, non-executable bit. Unfortunately, all other pages, including non-paged pool, are actually executable for unknown reason. But at least they are getting closer. NetBSD implements code data separation as a result of WXRX policy. So the page is either writable or executable. Almost for sure OpenBSD also implements this, and I'm not sure whether FreeBSD implements it or not. And we also have PAX, which enforces code data separation, but as far as I know, only in user mode. I'm not sure if in kernel. It is? Okay, so does it use an NX bit on the 64-bit processors? Okay, because we all know that PAX on IA32 uses some segment tricks, right? Which couldn't be used in kernel probably. But I guess on 64-bit processor they already implement in kernel, right? Okay, so this is very good. So we see that this code data separation requirement is not that hard to achieve because all the operating systems are going into this direction. Code signing in operating systems today. Starting from Windows 2000, all system executables are digitally signed. This is very good. Vista x64 introduced the requirement that all third-party kernel drivers needs to be signed. Again, this is very good. Even though it's bypassable, it's still very good because it allows us to verify the code sections of the loaded drivers. NetBSD has a mechanism called veryexec. This mechanism doesn't work with digital signatures as of today, but they're actually planning to introduce to improve it to separate digital signatures. But what veryexec does is that it can associate a fingerprint with each executable, could be like a kernel module, and then once this is done, the kernel maintains this association all the time, and this is maintained on a page per page level. So this is very good for our verification algorithm. And as far as I know, NetBSD is the only operating system which allows for that right now. As far as I know, there's no built-in signing solution on Linux, only some third-party extensions. And on Solaris 10, ELF signing has been introduced, which is similar to PE signing on Windows. So again, we see that cat signing is not a hard requirement to meet. So NetBSD, I created this slide on NetBSD because I'm in touch with Alat Efrat, which is one of the NetBSD developers, and we are thinking seriously about implementing those requirements in NetBSD and implementing some kind of proof of concept of a verificator. So currently, as I said, NetBSD has this code data separation and also has this code signing, code verification on per page level. But still, memory reading is a problem which is not solved. The biggest problem is actually, if we consider a software solution, is the mapping of CR3 register to virtual address. Reliable mapping. Yep. Okay, so now imagine we created this verificator, let's say for NetBSD. So this is a piece of program that would be a loadable kernel module for sure. So just a piece of program, a bunch of assembler instructions, which does some actions and then produce some result. So of course, if attacker knows the binary, have access to binary of this detector, it can prepare attack which subverts this very binary in some way by patching some instructions, like some final if instruction, which is going to display the verdict, right? You've got two programs running at the same privilege level. One can patch the other one if this knows this program exactly. So there was a Hacker Defender project a few months or more ago, and they actually were selling commercial version of Hacker Defenders which contained those implementation-specific attacks against particular detector on the market. One idea to mitigate it is to have detector or verifier located in hypervisor, ring -1. So provided we can prevent anything other from loading into hypervisor, this could be pretty safe solution. Another would be to use a hardware-based memory access, but we have this problem with page.memory. Finally, you're not gonna like it, but I think this is a acceptable solution in practice. We just need to have a non-public detector. If we have a non-public detector, then an implementation-specific attack is not possible against this detector. Only generic attacks are possible. Okay? Yeah. The question was, okay. Okay. Yeah. Yeah. Okay. I'm gonna comment on this. Okay. So he said that it's not really true that we cannot read paged-out memory using hardware, because we can set up a DMA transfer, or we can, well, let's say not DMA, but let's say we can talk directly to SCSI controller or this controller, right? This is unfeasible for several reasons. One reason is this is very complicated and it's very OS specific. This could be probably implemented against open source software operating system where we know the format of page file. But for example, Microsoft doesn't make the format of page file available, so we could not read. We cannot understand it. Of course, somebody can say, well, we can reverse engineer it, but well, this is not the proper way of doing this. Another way is that we cannot be sure that actually rootkit didn't modify the operating system to use different kind of paging. So we would be reading something which we think, right, is used for paging, but in fact, the paging would be in some other place.
But you have the page registers, you can read the page registers, you can read the data from the list.
What is page register?
We have the MNU, and it has registers where are pages. So you can read the registers from
No. I'm not quite sure if I understand you. Okay, I'm gonna give you a microphone. Just a second.
Okay, the idea was to have a special Linux box, for example, that says I use the device driver on the machine that is to be examined. So I access via firewire, for example, if the whole 4 gigabytes of address space is available to me, I access the via firewire the PCI card from maybe a SCSI controller or something. So I know by scanning the PCI config space, there is a PCI controller, maybe a Adaptec, something. I set up a transfer to read the devices. So I know there are devices, I can do all the kernel stuff, all that stuff that the kernel does normally. So I know there's a drive and there's a SCSI controller, and I know there's a partition where page files normally are, and I read this partition, for example. So I know everything that is paged out, I can access the memory, and I can also access the CPU.
Yeah, but you don't know whether the kernel was modified to actually use different page file, right? So you would be reading the page file which the healthy kernel would normally use for paging, but in fact the kernel was just subverted and is using some kind of different page file. Like, I don't know, the mapping is quite different, right?
Okay, but I can also read the kernel from disk, and I do some offline forensics and read the kernel.
Now you can't do this because the modifications in kernel could be non-persistent. They could be only in memory and not on disk. No, because there is no way how we can verify actually that we can only read code memory to make sure, and you cannot know for sure that there is not type 2 malware which could modify kernel paging in such a way that we'll be using different paging, right? The point is that does it work? Yeah. The point is that okay, we can read as I said, it's not a problem. We can read the whole memory. So you see the 4 gigs of memory, but you don't know anything about this memory, how it should look like. You can only verify code, but that might be some modification inside kernel data, which makes the paging is behaving differently. Okay, I think we'll make question sessions just after the end of the lecture, and I still have a few slides to show. Okay. Okay, so now does this microphone work? Actually, yes. So now imagine that we have solved all those problems. Let's say we have this hardware-based memory reading. We have this. We don't care about ISA attacks, implementation-specific attacks. Operating system vendors changed their operating system to follow those requirements, so everything is fine, right, with type 1 and type 2 malware detection. Unfortunately, this doesn't mean the end of the battle, because we have something which I call type 3 malware. And type 3 malware is kind of similar to type 0 malware in the way that it doesn't introduce any modifications into the operating system memory or registers. It just sits aside, right? But still is able to control all the operating system applications running. When I was presenting this classification 1 year ago at Black Hat Federal, I didn't know about type 3 malware that is possible to implement. Only a few months later, I implemented Blue Pill, which is actually an example of this. So there are 2 examples actually, Blue Pill and Vitriol, which was implemented by Dino Daisovi, almost at the same time as I implemented Blue Pill, completely independently. It's very funny. And Blue Pill uses Pacifica AMD technology, AMD Pacifica technology, virtualization technology, while Vitriol uses Intel VTX technology. This is not going to be a lecture about Blue Pill. I gave several lectures about Blue Pill already, so I'm not going to go into details of how it works. Basically, it works in the way that it runs on the native system, it creates a hardware virtual machine, it moves the running operating system into the hardware virtual machine, and itself, it becomes a hypervisor. This all happens on the fly. It takes like less than 1 millisecond to do all of this. And the native operating system, which is now guest operating system, doesn't even realize that it has just been moved into the virtual machine. Second? How is what? Yeah, this is what I discussed many times during my Blue Pill talk. The performance impact as an experience for the user is 0. There are some instructions which are intentionally intercepted by hypervisor, like read MSR instruction, which presents some impact which could be used for time-based detection of Blue Pill. But there are several problems with it in practice. One problem is that we need a trusted time source. The other problem is that we almost done this actually on a generic way of cheating timing analysis without cheating timers. Right? So basically the effective performance impact is 0 because this is hardware virtualization. Second? I'm sorry, we're going to discuss it later with a microphone in the audience, okay? So timing analysis is one theoretical way to detect it. As I said, it's not practical, and as I said, we have almost completed an improvement for Blue Pill which allows to resist timing analysis. Detecting side effects. We could look at network communication. Again, this could be very challenging if this type 3 malware uses some kind of advanced cover channel, like Nushu, for example. And also we can look at disk usage, or we can analyze PCI-ROM or BIOS in case it was implemented as persistent memory. But actually then it wouldn't be type 3 malware, then it would be type 1 malware. So in ideal case, when it's actually a non-persistent malware, well, the disk usage, analyzing disk usage doesn't help much. So I don't know any feasible way to detect type 3 malware today in practice. We might imagine that the particular implementation of virtualization, I don't know, Pacifica SVM revision 1.2, for example, contains some implementation bugs which could allow for creating a detector to detect the presence of a hypervisor. Most likely they do have such bugs. So we could think of some kind of red pills for Pacifica, for VTX. But this is far from being a systematic way of verification, right? This is just a hack. They might just fix the problem and it wouldn't work on future processors. And we need a systematic way. So the only way I think it could be used systematically against Blue Pill would be a hardware-based well, basically it would be introducing a new instruction to SVM or to VTX. Well, let's say it's SVM check. Let's say it's SVM check. And of course, this instruction doesn't exist today. But let's say we need this instruction to detect hypervisors in a generic way. This instruction would work like this. It would require some password, which would be processor specific, model specific. And then it returns 0 or 1, depending on whether it's executed inside hypervisor or or in a native mode. Password should be different for every processor, so every user gets a password and a certificate when gets a new processor. Or it's displayed in BIOS post screen when computer boots. This is to prevent creating generic programs which behave differently on inside virtual machine and outside virtual machine. Because sometimes we might. Why is this important? Sometimes it's important. It's mostly important for antivirus industry, I would say, because they want to analyze malware inside virtual machine, and not lots of, but some malware today, for example, they try to actively detect the presence of not hardware hypervisors, but software hypervisors like VMware. So they try actively detect it and then to behave differently inside VM and outside VM, right? So actually, this is not that. This is quite logical that we might want to prevent this to happen. And this password could be entered to the antivirus program during installation, then could be used only by this program to detect whether we are blue-pilled or not. A few words about kernel protection versus hypervisor protection. Because what we can do today, actually, we can only do hypervisor protection. So we can create something similar to blue pill, load it into kernel and load it into the system so that it will block all the other hypervisors from loading. This is actually not that easy as it sounds. Actually, it's easier to create blue pill rather than anti-blue pill hypervisor for several reasons, DMA access being one of them. But this is feasible in my opinion. In contrast to kernel protection, which we can never guarantee 100% because kernel is huge, and also we have all those third-party kernel drivers, which could contain buffer overflows. This doesn't apply to hypervisor. We can have very little Kotlin hypervisor. So this is feasible, but so far nobody has created such a product as far as I know. Okay, so the bottom line is, Type 0 malware is beyond the scope of my research because it's not something which compromises systems. Type 1 malware is relatively easy to fight today. Type 2 malware is a challenge, and we cannot solve this type 2 malware problem without the help of operating system vendors. Implementation-specific attacks are always possible against software-based detectors, but we can mitigate those attacks in practice by using hardware-based detector or hypervisor-based detector or custom private detector. Systematic verification against type 3 malware seems to be unfeasible today and seems to be feasible only if CPU vendors introduce special instruction like this SVM check, which I just showed. Prevention against type 3 malware seems feasible, but as we know, prevention is never enough. When reading eWeek a few days ago, I found the 10 key predictions for 2007, and prediction number 5 was that by the end of 2007, 70% of enterprises will be infected with undetected, financially motivated, targeted malware that evaded their traditional perimeter and has defenses. So, can the good guys win? No, without the help of us vendors. And who can we trust? For sure not our operating systems. Some credits and questions.
Okay, we will take a few more minutes for question and answers. We have the first question here at the microphone. Please come here and queue if you want to ask a question, as we only have one microphone at the moment. Thank you.
Yeah, hardware-based memory reading looks promising, but you have two problems even if you disable paging on the machine.
Okay.
As far memory reading does help nothing if you don't have the state of the MMU table, and the MMU table is cached in the processor.
Well,
So you want?
I don't really need to have, because the state of this table is just physical to virtual mapping. I don't really need that as far as I can make sure that all executable pages are, okay, as far as I can find out whether the page is executable, and second, whether I can verify the code on it. But as I just was talking about this, I found out that, I realized that you might be right that I might not be able to find out whether the particular page is executable or not without reading this. Yeah,
Yes.
that's a good point.
And you didn't see the true state in memory. The true state you have only in CPU. And if you cannot take a hardware look at the CPU,
What do you mean true state?
The true state of the MMU state of the MMU translation table. It's cached
No,
in.
the only thing I need actually is to find out the attributes of a given physical page, whether
Only
it's
that-
executable or not,
If
and its contents. This is all I need. But as you pointed out, I might not be able to find out whether it's executable or not by just using DMA access. That might
Yes.
be true.
And
because I might. No, but on the other hand,
they might the translation table may change in the CPU and is not written back to memory. So you have the CPU sees another mapping of memory as your DMR device.
okay, yeah.
You have to
I agree.
interpret.
Yeah.
You have to interpret.
That's a good point. Without but I don't care about mapping. I just care about attributes of pages.
Okay, that's one point. And another point is next generation CPUs got an I/O MMU.
I know that. Yeah.
And so you what is calling?
Yeah,
you can hide
remap.
physical memory from DMR devices.
IOMMU is a different thing. Yeah, I know that.
Also,
Yeah, but
it
it's a good
doesn't
point.
help. It doesn't help so much.
Yeah, and also as I just noticed, we can cheat hardware-based memory access also in some different ways.
You need help from the CPU. More help.
Yeah. Okay, thank you very much. That was very good. Any more questions? No.
Yes, there are questions.
Sure.
One question is regarding the hypervisor. I'm not sure if the newest CPUs even have the JTAG feature. Normally, every CPU has a JTAG interface to do some debugging stuff. So it would be possible to hook the JTAG to some magic hardware on the computer, so I can read the registers via JTAG, so I know
You want to read what?
the registers.
The registers of CPU.
Yes, and
via,
so I can-
via JTAG interface.
Yes. So I can. Yes, but that's not the problem. So I hold the computer, read the JTAG thing, and then I know what is going on or not.
Well, this would be great, but I'm not sure if it's possible. I mean, do you know? I mean,
Depends on the CPUs.
Yes, but if, for example, I know it from the PowerPC, it's possible to read them at a speed of maybe.
is it?
Huh? PowerPC.
Yeah.
Yes, it's possible to read via JTAG, and I think it's had 30 megahertz or something. But so you can read some registers, and you have to hold the CPU just for a small time.
Okay, that's interesting. That's very interesting.
But so I think these debuggers also. I know if the Pentium 3 has such JTAG debugging feature. I'm not sure if modern CPUs have it. You have to read the data sheets. Mostly they are under NDA, so you have to wait until you get the data sheets. Another thing regarding the.
But so this PowerPC, does it use Hyper Transport? Or how is it connected?
JTAG is a standard that has some pins, and you can say.
It's a PCI standard, right?
No, JTAG is the JTAG standard. It has some pins, and you can use it to test hardware. For example, you can say, put this pin on high or on low, so you can know if it's soldered properly, or you can, for example, program FPGAs via JTAG, so it's very, or CPLDs are programmed with JTAG. You can interfere with hardware via JTAG. So you can interfere to your CPU and ask, hey CPU, give me your registers, and you can read them like a big shift register. The JTAG chain is a big shift register that is implemented on the hardware.
Yeah, okay, but let's say you're a PCI card which wants to do that. So this PCI card needs to use some PCI command packet to the PCI packet to be translated to JTAG packet, to JTAG interface, right?
Now you will need a special piece of hardware to read the JTAG, because normally the JTAG pins are not connected.
Okay.
So you need some debugging things, like if you, for example, you develop embedded systems, you have JTAG to read some things. For example, if you want to open your router and it says some Linux and you cannot open it, you take the JTAG device and you can read everything, and you know how it works, or you can execute code via JTAG. It's deadly slow, but it works.
Yeah, but,
so,
but actually you cannot just plug something into your PCI slot, which would be able to read JTAG, right? To communicate over JTAG interface with processors. Or
yes,
can you?
It would be possible with some soldering.
Wait, what?
With some soldering.
Okay, so this is not possible in practice.
Yes, but another thing is, you said that it's not possible to read the table of the MMU. So I would suggest to put some code via DMA inside the stack segment, and this code will be executed then, and that code reads the setting of the table.
How can you make sure? Okay, how can you make sure that this code will be executed?
Because I know the setting of the stack pointer.
Oh, you want to override the current code at the instruction pointer with your code, right?
Yes, I have a small monitor program that I put into the stack, so I can wait for this program to be executed.
Okay.
This program gives me some information, probably on the stack, so I can read the information, so I know what was there. Then I override the faked code with the original backed up code, and so it works again.
Yeah, that's interesting.
So this would be a small thing, because if I have my bad Linux device that uses the devices of the other computer, it would also be possible to write some monitor code inside the executed RAM. So another thing, you said that it is not possible to, let me think. Yes, the type 1 things. You have said that it's. I have to think a moment. Okay. Okay, so he can, because I have to think a small bit.
I don't know. Maybe we can. Maybe we can finish this lecture, and I would just go downstairs and we can just talk directly, right? Because like nobody's listening to us.
The only question that I have is, how do you think about that you can like identify the virtual machine through? Okay.